A common impulse situation is considering cars when they come to sudden stops. There's two equations for impulse. Impulse we can find by considering the force and the time, or impulse we can find considering the momentums. And momentum is always mass times velocity. So what you have to do really is look at the question and see what you got the most of. In this question, I can get impulse because I know about the masses and the velocities. So I'm going to say impulse is delta momentum for this case, and that's going to be mv2 minus mv1. The masses aren't changing, that's a constant mass. We've got a person traveling at 15, so here I'll just plug in numbers. So our J is going to be our 65 kilogram person. It ends up that they're not moving, they're at rest. And initially our 65 kilogram person was going 15. Multiplying that out, we get a momentum of 975. It's going to be negative because it's kind of backwards compared to the 15. All these things are vectors. It's got funny units. Because we found it based on momentum, its units are going to be kilograms times meters per second. If we worked in the industry of studying car crashes, that 975, the fact that it's that big might have some significance. As I first go through it, that seems like a big number, but how impulse affects things, what force it generates, as you'll see in the next part, really depends on the time. So moving forward, we now know that impulse is this negative 975 number. We also know that impulse is force multiplied by the time the force acted for. So if we've got more data, if we know about the time, we can use that to calculate the force. And this one I made up, the time was 0.2 seconds. So F is going to be negative 975 divided by the time. The time I made up was 0.2. By the magic of the metric system, this is going to convert into a force units, a number in newtons. I got a value of 4875. 4875 newtons. The negative just meaning backwards compared to the original speed, the original velocity of 15. I added a little bit to the question. What if the car didn't have airbags? What if it took less time for them to stop? That kind of comes out of this part here. If I write it in letters, F is going to be our delta momentum over delta time. We've got an inverse relationship between force and time. If we're considering a collision, so a particular change in momentum, if the momentum's not changing, like in this question, it was the 975 number. If that change in momentum isn't changing, if that's constant, then we've got an inverse relationship between force and time. If the time were to decrease for some reason, maybe there's no airbag, so you come to a sudden stop, bouncing off the steering wheel or windshield or dashboard. If the time decreases, then the force is going to increase dramatically. That little bit there, the force connected to time, that's a lot of what the engineering behind making safer cars is all about. Add airbags, add crumple zones, modify seatbelts so they have a little bit of stretch to them. Engineer things that increase the amount of time that an object comes to a stop and that decreases the force. Similarly, like you would know that if you've ever jumped off something high, you never want to land with rigid legs. Rigid legs means a short time period. Short time period means large force. Whenever you can absorb something's impulse over more time, that's going to require less force.